Close your eyes and let yourself drift back through time, back beyond your lifetime, back through centuries and millennia, back through ages so vast they dwarf human history, until you arrive at the very beginning. The universe is about 13.8 billion years old, beginning from an extremely hot, dense state known as the Big Bang. Imagine that moment, if you can call it a moment, when everything that would ever exist was compressed into a space smaller than you can picture. All the matter, all the energy, all the potential for stars and galaxies and planets, all of it together waiting. And then, in an instant beyond instants, it began. Let your mind rest on this threshold between nothing and everything. In the first tiny fraction of a second, a sliver of time so small it has no meaningful comparison in your daily life, space itself expanded extremely fast during a period called inflation. Not an explosion into space, but space itself unfurling, stretching, growing at speeds that make light seem to stand still. You might picture it like the surface of a balloon expanding, but even that doesn't capture it fully. Every point moving away from every other point, the fabric of reality itself spreading outward in all directions at once. This happened so quickly, so incredibly fast, that in less time than it takes a particle of light to cross an atom, the universe grew from something unimaginably small to something cosmic in scale. And as you float through this moment in your imagination, notice something remarkable. Inflation made the universe smooth and nearly the same in every direction. Like cream stirred into coffee until no swirl remains, this rapid expansion smoothed out any irregularities that might have existed. When you look up at the night sky, when you gaze out in any direction across the cosmos, you're seeing the legacy of this smoothness. The universe doesn't have a center, doesn't have an edge you could find. It's remarkably uniform, wonderfully consistent, stretched into harmony by those first fractions of a second. Rest in that uniformity, that cosmic sameness that surrounds you from every direction. During this first instant, something else was taking shape, something that would determine everything that followed. The basic forces of nature took the forms we recognize today. Gravity, which holds you gently to the Earth and keeps planets in their orbits. Electromagnetism, which creates light and binds atoms together. And the nuclear forces that hold the hearts of atoms together or let them break apart. These forces, which seem so different from each other now, may have been unified in that earliest moment, all one force, one fundamental interaction. But as the universe expanded and cooled, just slightly, they separated like streams branching from a river, each taking on its own character, its own strength, its own role in shaping reality. These forces, born in that first instant, are still at work now, in the gentle pull of gravity you feel, in the light touching your eyelids, in every atom of your being. And through it all, through this explosive birth and rapid expansion, the universe was filled with intense energy and radiation, far hotter than anything we see now. Not the warmth of sunlight on your skin or the heat of a fire, but a heat beyond heat, a temperature where matter as we know it couldn't exist yet. Only pure energy, raw and brilliant, filling every point of the expanding space with a glow more intense than the core of any star. Slowly, gently, as space continued to grow, this heat began to spread out, to thin, to cool, like a bath slowly losing its warmth. But in that beginning, everything was light, everything was energy, everything was possibility waiting to unfold. And from that infinite warmth and light, everything you know would eventually emerge. Rest now in that thought, that you are made of matter that once existed as pure energy in that first brilliant dawn of time. Let time move forward now, just slightly, just 1 second into the existence of everything. 1 second. In your life, A second passes in a heartbeat, in a breath barely noticed. But in that first second of the universe, everything was changing. About 1 second after the Big Bang, protons and neutrons formed from smaller particles. The universe had cooled just enough, though it was still unimaginably hot, for these fundamental building blocks to hold together. Quarks, those even tinier particles that had been dancing freely in the heat, now bound themselves into partnerships, forming the protons and neutrons that would become the foundation of all matter. You can picture them coming together like dancers finally finding their partners, settling into formations that would last billions of years. Every atom in your body contains these particles, born in that first second, still holding together after all this time. And the universe didn't pause to rest. Over the next few minutes, just minutes, a span of time shorter than it takes to boil water, these particles fused into the first nuclei of hydrogen and helium. Imagine the simplest possible construction project: protons and neutrons finding each other in the cooling cosmic soup, pressing together, sticking, forming the hearts of atoms. Hydrogen nuclei, the simplest, just a single proton standing alone. Helium nuclei, slightly more complex, with 2 protons and typically 2 neutrons bound together in a tight embrace. This was matter organizing itself for the first time, taking the first steps toward complexity. The temperature was still millions of degrees, still far too hot for electrons to settle around these nuclei, but the seeds of atoms were being planted in those precious early minutes. This remarkable moment in cosmic history has a name. This process is called Big Bang nucleosynthesis. Let the word settle in your mind. Nucleosynthesis, the creation of nuclei. It happened everywhere at once, throughout the entire expanding universe, as natural and inevitable as water freezing when the temperature drops. No laboratory could recreate these conditions. No human technology could achieve what the cooling universe did effortlessly in those first minutes. It was chemistry before chemistry, physics writing the rules that would govern everything to come. And it happened in darkness, because light itself couldn't travel freely yet, scattered constantly by the dense fog of particles filling space. What emerged from those first minutes became the foundation of everything. Hydrogen and helium became the most common elements in the universe. For every 10 atoms in the cosmos, imagine about 9 of them are hydrogen and 1 is helium, with just the tiniest fraction being anything else. This ratio, set in those first minutes, remains true today. When you look at the sun, you're seeing mostly hydrogen and helium, still following that ancient recipe. The giant clouds between the stars, the vast reservoirs of matter floating in space, mostly hydrogen and helium. These 2 simple elements, forged in the universe's infancy, became the most abundant substances in existence. They are the cosmic default, the baseline from which everything else emerged. Rest in the simplicity of it. Just 2 main ingredients filling the universe. And here's something wonderful to contemplate as you drift towards sleep. Almost everything else came much later. The carbon in your bones, the iron in your blood, the oxygen you breathe, the calcium, the nitrogen, the phosphorus. None of these existed yet. For hundreds of millions of years, the universe would remain a place of elegant simplicity, just hydrogen and helium, and almost nothing else. All the heavier elements, all the rich diversity of the periodic table, all the materials that make planets and people possible, these would have to wait. They needed something the early universe didn't yet have. They needed stars. But for now, in these first minutes and the long ages that followed, the universe was a simpler place, quieter, waiting patiently for the next chapter to begin. And in that waiting, in that cosmic pause, there was a peaceful kind of patience, the patience of something infinite, something that had all the time in the world. Now let yourself drift forward through time, through long ages of waiting, through 380,000 years of patient expansion and cooling. In cosmic terms, This is barely a moment, but imagine it in human time scales. Longer than all of recorded history, longer than humans have walked the earth, longer than our species has existed. And throughout this vast stretch of time, the universe was dark, or rather opaque, filled with a glowing fog so dense that light couldn't travel more than a tiny distance before bouncing off another particle. But change was coming, slowly, inevitably. About 380,000 years after the Big Bang, the universe cooled enough for electrons to join nuclei and form neutral atoms. Picture it like a cosmic storm finally calming. Electrons, which had been flying free and wild through space, now settling down, finding their orbits around nuclei, completing the atoms that had been waiting all this time. Hydrogen atoms, helium atoms, whole and complete at last. The temperature had dropped to a few thousand degrees. Still hot enough to glow, but cool enough for matter to take this gentler, more stable form. And with this transformation came something magnificent. Light was finally able to travel freely through space. Imagine curtains suddenly opening in a dark room, or fog lifting on a morning hillside. For 380,000 years, light had been trapped, constantly scattered, unable to move more than a short distance before colliding with a free electron. But now, with electrons bound safely in atoms, space became transparent. Light could travel unimpeded, racing across the expanding universe, carrying information about where it came from, when it was born, what the universe looked like in that ancient moment. This was the universe's dawn in a very real sense. Not the first moment of existence, but the first moment that light could truly shine across the cosmos. Take a breath and rest in that image. The universe becoming clear, becoming transparent, light streaming freely for the first time through infinite space. That light is still traveling. This ancient light is now seen as the cosmic microwave background, or CMB. It has been journeying through space for more than 13 billion years, stretched and cooled by the expansion of the universe. Shifted from the visible glow, it once was into microwave wavelengths that our eyes can't see, but our instruments can detect. It surrounds you right now, this ancient light, coming from every direction equally, the whisper of the universe's infancy still echoing through space. If you could see in microwave wavelengths, the whole sky would glow with it, a gentle, nearly uniform warmth filling every corner of the heavens. It's like finding an old photograph, faded but still legible, showing you what the universe looked like when it was young. This light has traveled farther and longer than almost anything else we can observe, crossing the entire visible universe to reach us here, now tonight. In fact, the CMB is the oldest light we can observe. Nothing we can see with telescopes or any instrument comes from an earlier time. Before this light was released, the universe was opaque. We can't see through that fog, can't observe anything from those first 380,000 years directly. So this cosmic microwave background is our horizon, our limit, the furthest back we can look. It's the universe's baby picture, the earliest snapshot we have. When astronomers study this light, they're seeing the universe as it was when it was less than 1/4000th of its current age, a cosmic infant taking its first clear breath. And there's something deeply peaceful about that, about knowing that this ancient light is still here, still traveling, still carrying its message across the vast distances between then and now. And that light tells us something wonderful. Tiny hot and cold spots in the CMB reveal small density, bumps in the early universe. The light isn't perfectly uniform. It's almost uniform, smooth to an incredible degree, but not quite. There are variations, tiny differences in temperature of only a few thousandths of a degree, creating a subtle pattern across the sky. These aren't random. Each slightly warmer spot marks a place where matter was just a little more dense, a little more concentrated. Each cooler spot marks a region that was slightly emptier. These tiny ripples, these gentle undulations in the fabric of the early universe, were the seeds of everything to come. Where matter was slightly more dense, gravity could begin pulling more matter together. Over millions and billions of years, these small differences would grow, would amplify, would eventually become the galaxies, the clusters of galaxies, the vast cosmic web of structure we see today. You are made of atoms that once resided in one of those slightly denser regions, atoms that responded to gravity's gentle call billions of years ago. Let yourself imagine those tiny ripples in that ancient light, those subtle variations that made everything possible, and feel yourself drifting on those primordial waves, floating peacefully in the memory of the universe's early dawn. And now, as that ancient light streamed away in all directions, the universe grew dim. After the first light faded, the universe entered a cosmic dark age. The brilliant glow that had filled everything cooled and shifted into wavelengths too faint to illuminate anything. The stars had not yet been born. There were no galaxies spinning in the darkness, no brilliant nebulae painting the void with color, no supernovae flashing their brief, intense light. If you could have floated in space during this time, though of course, nothing like you could exist yet, you would have seen only darkness stretching in every direction, broken by no pinpoint of starlight, no distant galaxy's glow. It was a time of waiting, a cosmic pause between the brilliant beginning and the luminous age to come. Rest in that darkness for a moment. Not a frightening darkness, but a peaceful one, like closing your eyes and feeling the quiet stillness of a world at rest. This period of darkness was not brief. This dark age lasted about 200 million years. 200 million years of quiet expansion, of gradual cooling, of matter drifting through space in the dark. To put this in perspective, 200 million years ago on Earth, dinosaurs were just beginning their reign. That's how long the universe waited in darkness, patient and unhurried, following the slow rhythms of gravity and expansion. Stars would come, galaxies would form, light would blaze again across the cosmos, but not yet. For now, the universe was content to be dark, to be simple, to let time pass slowly like a long, peaceful night. There's something almost restful about imagining such a vast stretch of time where nothing dramatic happened, where the universe simply was, expanding and cooling in its own gentle way. But the universe was not empty during this time. There were no stars or galaxies yet, only vast clouds of gas. Hydrogen and helium, those elements forged in the first minutes, spread throughout space in enormous, diffuse clouds, thinner than any vacuum we can create on Earth, yet stretching across distances that dwarf anything we can easily comprehend. These clouds filled the expanding universe, invisible in the darkness, cool and neutral, barely interacting with themselves or with anything else. Imagine fog so thin you wouldn't know it was there, spread across not just a valley, but across what would one day become thousands of galaxies. This was the raw material of everything to come. Every star, every planet, every atom in your body existed then as part of those dark, quiet clouds, waiting patiently in the cosmic night. Yet even in this stillness, change was happening, slowly and inevitably. Gravity slowly pulled this gas into denser clumps. Remember those tiny variations in density, those gentle ripples from the cosmic microwave background? They were still there, still present, and gravity was responding to them, amplifying them grain by grain. Where gas was slightly denser, it pulled on the gas around it, drawing more matter in, becoming denser still. These weren't dramatic collapses. Not yet, but rather a gradual gathering, a patient accumulation, like dust settling over centuries in some forgotten place. The clouds began to develop structure, to form threads and filaments, to concentrate in some regions while other regions grew emptier. This was architecture on the grandest scale, the universe organizing itself through the simple, persistent pull of gravity, working in darkness, but working nonetheless. And chemistry was happening too, in its own quiet way. Simple molecules like helium hydride formed and helped the gas cool. When atoms came together to form molecules, helium and hydrogen bonding in that primordial darkness. They could radiate away energy more efficiently than single atoms could. This cooling was crucial, gentle but important, allowing the densest regions to contract more easily, to compress without bouncing back, to continue their slow collapse toward what would eventually become stars. These were the very first molecules in the universe, the first chemical bonds, the first step beyond simple atoms toward the complex chemistry that would one day make life possible. Even in the darkness, even in the cold, even in the apparent emptiness, the universe was preparing itself, setting the stage for the brilliant age of stars that was slowly, inevitably approaching. Let yourself drift with that patient preparation. Feel the slow pull of gravity, the gentle cooling, the vast dark clouds slowly gathering themselves together, and know that from this peaceful darkness, light would soon emerge again. And then, after those long ages of waiting, something remarkable happened. The first stars, called Population 3 stars, formed a few 100 million years after the Big Bang. In the densest regions of those gathering gas clouds, where gravity had worked most effectively, the hydrogen and helium compressed and compressed until the centers grew hot. Hotter than anything since the Big Bang itself. Until finally, nuclear fusion ignited. Imagine the first spark in that cosmic darkness, the first point of light breaking through after 200 million years of night. And then another spark, and another, scattered across the universe as gravity found enough material in countless places to kindle these first stars into being. They were not like our sun, these ancient pioneers. They were made purely of hydrogen and helium, untainted by heavier elements because none existed yet. They were the universe's first attempt at stars, original and unique, never to be repeated once heavier elements entered the cosmic mix. These primordial stars were giants beyond our easy comprehension. These stars were huge, bright, and short-lived. Where our sun is modest in size, these first stars were often 100 times more massive, even 200 times more massive, burning with a brilliance that would make our sun seem like a candle beside a searchlight. They blazed blue-white, fierce and hot, pouring out enormous amounts of energy into the darkness around them. But their very size and brightness meant they could not last. Like fires that burn too hot, consuming their fuel rapidly, these massive stars lived fast and died young. Where our sun will shine for 10 billion years, these first stars might last only a few million years, a cosmic eye blink. They burned through their hydrogen at furious rates, desperate and beautiful, transforming the primordial elements in their cores, creating through fusion the first heavier elements the universe had ever known. Carbon, oxygen, silicon, iron, all forged in the nuclear furnaces of these ancient giants. And their light changed everything. Their light began to heat and transform the universe again. As these first stars shone, their ultraviolet radiation streamed out into the surrounding gas, energizing it, ionizing it, breaking apart the neutral atoms that had formed so long ago. This process, called reionization, gradually cleared the cosmic fog once more, making the universe transparent in new ways. The light from these stars could travel farther, illuminate more, transform more. Bubbles of ionized gas expanded around each star and cluster of stars, eventually merging together, until over hundreds of millions of years, the entire universe shifted from neutral back to ionized. It was like dawn breaking not in one place, but everywhere at once, gradually, as more and more stars ignited and their collective light pushed back the darkness. The universe was waking up, growing warmer again, becoming energized and active after its long, cold sleep. The stars did not remain isolated for long. Groups of stars gathered to form the first galaxies. Gravity worked on larger and larger scales now, pulling not just gas but entire collections of stars together into bound systems. These first galaxies were smaller than the great spirals and ellipticals we see today, more like building blocks that would later merge and combine. They were irregular in shape, chaotic and young, thick with gas and dust, and blazing with the light of massive stars. Imagine them scattered through space like islands of light in a vast ocean, each one a collection of millions of stars bound together by gravity, each one a factory for creating new stars from the remaining gas. Some grew by pulling in more gas from their surroundings. Others collided and merged, their stars mingling, their gas clouds crashing together and igniting new bursts of star formation. The universe was becoming a livelier place, a place of structure and complexity, no longer just empty clouds but organized systems, the first great architecture of matter. And at the hearts of some of these young galaxies, something mysterious was taking shape. Some young galaxies developed supermassive black holes at their centers. Not the small black holes that form when stars collapse, but monsters millions or even billions of times the mass of our Sun, concentrated in regions smaller than our solar system. How they formed so early remains one of cosmology's deep questions. Perhaps they grew from smaller black holes that fed voraciously on the dense gas around them. Perhaps they formed directly from the collapse of enormous gas clouds. Whatever their origin, they were there, lurking in the centers of these infant galaxies, shaping the orbits of stars around them, sometimes feeding on infalling matter and blazing as quasars, the brightest objects in the universe, visible across billions of light years. These black holes and their galaxies would grow together over cosmic time, evolving in tandem, each influencing the other. And as you imagine these first galaxies taking shape, their stars glowing, their black holes spinning silently in the dark, let yourself feel the universe coming alive, growing complex, beginning its long journey toward the rich, structured cosmos we see when we look up at the night sky. The light from those first stars, and their descendants, did more than simply illuminate the darkness. Bright stars and quasars caused a phase called reionization, changing hydrogen gas across space. Imagine waves of energy spreading outward from every star, from every brilliant quasar powered by a feeding black hole, each wave pushing into the neutral hydrogen that still filled the spaces between galaxies. These energetic photons struck hydrogen atoms, stripping away their electrons, transforming them from neutral and invisible to ionized and reactive. This wasn't a sudden shift, but a gradual transformation spread over hundreds of millions of years, like the tide slowly coming in across a vast shore. Bubbles of ionized gas expanded around each bright source, growing and overlapping, merging together until the entire universe had shifted states once more. The gas between galaxies became ionized, and has remained so ever since, a permanent change written into the fabric of the cosmos by the light of those early stars. Let yourself imagine that transformation washing over the universe like a gentle wave, changing everything it touches, bringing a new clarity, a new transparency to the cosmic ocean. But the stars were doing something even more profound inside themselves. Inside stars, hydrogen fused into heavier elements like carbon and oxygen. In their cores, where temperatures reached tens of millions of degrees, hydrogen nuclei crashed together with enough force to overcome their electric repulsion, fusing into helium and releasing tremendous energy. This was the same process that happened in the first minutes after the Big Bang, but now it was happening steadily, continuously, inside countless stars scattered across the universe. And the massive stars didn't stop at helium. As they aged and their cores grew hotter still, they fused helium into carbon, carbon into oxygen, continuing up the periodic table, building heavier and heavier elements layer by layer like a cosmic onion. Neon, magnesium, silicon, sulfur, each element requiring higher temperatures, each step releasing energy that held the star up against gravity's inward pull. These stars were alchemists, transforming the simple elements of the early universe into the rich diversity of the periodic table, creating the building blocks of complexity, one fusion reaction at a time. And then came the moment of return. When massive stars exploded, they spread these elements into space. A star that had spent millions of years building up layers of different elements in its core would reach a breaking point when it tried to fuse iron. Iron fusion consumes energy rather than releasing it, and the core would suddenly collapse, triggering a supernova explosion of almost unimaginable violence. In seconds, the outer layers of the star would be blasted into space at a significant fraction of light speed, carrying with them all those carefully crafted elements. The explosion itself would create even heavier elements in its intense heat and pressure: gold, platinum, uranium, all the elements heavier than iron, forged in the chaos of stellar death. These elements would mix with the hydrogen and helium of interstellar space, enriching it, adding color and texture to the cosmic palette. Each supernova was like a flower bursting and scattering its seeds, ensuring that the next generation would be richer, more complex than the one before. And this process had profound implications. This cycle created the ingredients for planets and life. The carbon in your body, the oxygen you breathe, the calcium in your bones, the iron in your blood, all of it was made inside stars and scattered into space by supernovae. When new stars formed from gas clouds enriched with these heavier elements, they could create something impossible in the early universe: rocky planets. Worlds with solid surfaces, with atmospheres, with oceans. Places where complex chemistry could happen, where molecules could form and interact in ways that pure hydrogen and helium never could. The universe was slowly, generation by generation of stars, making itself capable of creating planets like Earth. And on at least one of those planets, in at least one corner of the cosmos, those elements would eventually organize themselves into something remarkable: life. You are made of stardust in the most literal sense, assembled from atoms that were forged in stellar cores and scattered across space by ancient explosions, gathered together by gravity into a planet, and eventually organized into the complex pattern that is you. Meanwhile, on the largest scales, structure continued to grow. Over billions of years, galaxies grew larger through mergers and gravity. Those small, irregular first galaxies collided with one another, their stars passing through each other harmlessly due to the vast distances between them, but their overall structures merging, combining, growing into larger systems. Two galaxies would approach each other, drawn by mutual gravity, dance around each other for millions of years, their shapes distorting, long tails of stars pulled out by tidal forces, until finally they merged into a single, larger galaxy. This happened again and again across the universe, building up galaxies from small to medium to large, creating the great spirals and ellipticals that dominate the modern cosmos. Our own Milky Way is the product of countless such mergers, assembled over billions of years from smaller predecessors. And this process continues still. In a few billion years, the Milky Way will merge with the Andromeda Galaxy, creating an even larger system. The universe builds on the grandest scales through patience and gravity, slowly assembling its greatest structures through cosmic time. Rest now in that image of slow, inevitable growth, galaxies like cities gradually expanding, the universe organizing itself into ever larger patterns, building the cosmic web we see today, strand by luminous strand. As you drift deeper into this cosmic story, let your awareness expand outward, beyond individual galaxies to the patterns they form together. Matter gathered into galaxy groups, clusters, and vast cosmic filaments. Galaxies weren't scattered randomly through space like stars sprinkled across a canvas. Instead, they organized themselves into a web of unimaginable scale, a cosmic web that stretches across the entire observable universe. Small groups containing just a handful of galaxies. Larger clusters with hundreds or thousands of galaxies bound together by their mutual gravity. And connecting these clusters, like bridges spanning cosmic voids, vast filaments containing chains of galaxies, walls of light-years-long structures threading through space. Between these filaments lie enormous voids, regions largely empty of galaxies, dark spaces in the cosmic architecture. If you could see the universe from outside, if you could view all its galaxies at once, you would see this beautiful lacework pattern, this foam-like structure of walls and filaments surrounding dark empty spaces, repeated on scales so vast they make galaxies seem like specks of dust. This grand structure didn't form by chance alone. Dark matter helped shape these structures by providing extra gravity. This mysterious substance, invisible to our telescopes, not interacting with light in any way we can detect, makes up most of the matter in the universe. For every atom of normal matter, the stuff that makes stars and planets and you, there are about 5 times as much dark matter, detectable only through its gravitational pull. It was dark matter that formed the scaffolding, the invisible framework around which normal matter could gather. The dark matter clumped first, guided purely by gravity, creating wells and valleys in space where normal matter would naturally flow, like water finding the low places in a landscape. Galaxies formed where the dark matter was densest, nestled in dark matter halos that held them together. Without dark matter, the universe would look entirely different. Galaxies might not have formed at all, or if they did, they would be scattered far more thinly, without the rich structure we see today. So as you imagine the cosmic web, remember that what you can see, the glowing galaxies, is only a fraction of what's there. The dark matter forms an even grander web that we sense but cannot see, supporting and shaping everything that shines. The timeline of all this structure formation is remarkable to contemplate. Galaxies formed within the first billion years of cosmic history. Think about that. In less than 1/13 of the universe's current age, the basic structures we see today were already in place. Those first small galaxies we imagined earlier, blazing with massive stars, appeared when the universe was only a few 100 million years old. By the time the universe reached its first billion years, galaxies were commonplace, dotting the expanding cosmos, already gathering into groups and forming the first filaments of the cosmic web. This was fast work on a cosmic scale, a period of rapid structure formation, driven by gravity, working relentlessly on the density variations that had existed since the beginning. The universe was young, dense, and actively building itself into the complex architecture that would persist for billions of years to come. Close your eyes and imagine the universe at this age, already recognizable, already structured, yet still young and evolving, still in its formative phase. Our own galaxy has its own story within this larger narrative. The Milky Way began forming a few billion years after the Big Bang. Perhaps around 13 billion years ago, in a region that was slightly denser than its surroundings, gas began to collapse and form stars in what would eventually become our home galaxy. At first it was smaller, less organized, more chaotic, a collection of gas clouds and young stars slowly being pulled together by gravity. The disk that we see today, the beautiful spiral structure with its graceful arms, formed gradually as the galaxy settled and organized itself, as angular momentum caused it to flatten into a spinning disk. The oldest stars in the Milky Way remember those early days, ancient globular clusters that orbit above and below the disk, containing stars nearly as old as the universe itself. These ancient stars are like fossils, preserving information about the conditions when our galaxy was young. And the Milky Way didn't form in isolation. It grew by absorbing smaller galaxies. Throughout its history, it has encountered dozens, perhaps hundreds of smaller galaxies that ventured too close. These smaller systems, unable to escape the Milky Way's gravitational pull, would be slowly torn apart, their stars absorbed into our galaxy's structure. This is still happening today. Streams of stars in the outer parts of the Milky Way mark the tidal remnants of galaxies consumed millions or billions of years ago, ghosts of ancient collisions. Our galaxy is a composite, built up over time from many smaller pieces, growing larger and more massive through cosmic cannibalism. And this growth continues. Right now, small satellite galaxies orbit the Milky Way, and some of them will eventually merge with us, adding their stars to our collection. The Milky Way is not a fixed, unchanging structure, but a living, growing system, still evolving, still building itself through the patient work of gravity over cosmic time. Let yourself imagine our galaxy slowly spinning in the darkness, adorned with hundreds of billions of stars, shaped by billions of years of growth and change, a beautiful island of light in the vast cosmic ocean. And know that you are part of it, here on a small planet orbiting one of those billions of stars, connected to this grand story, woven into the fabric of the cosmos itself. Now let time carry you forward, through billions of years of galactic evolution, through countless generations of stars being born and dying, through the slow accumulation of heavier elements in the Milky Way's gas clouds, until you arrive at a particular moment, a particular place. About 4.6 billion years ago, the Sun and Solar System formed from recycled star material. In one of the Milky Way's spiral arms, a cloud of gas and dust, enriched by the remnants of supernovae, containing all the elements built up over billions of years of stellar alchemy, began to collapse. Perhaps a nearby supernova's shockwave triggered it, or perhaps the cloud simply reached a critical density on its own. The cloud spun as it collapsed, flattening into a disk, and at its center, where most of the mass concentrated, temperatures rose until nuclear fusion ignited once more. The Sun was born, a perfectly ordinary yellow star, one of hundreds of billions in our galaxy, yet special to us because it became our star. The light that touches your face on a sunny afternoon is the light of a star born from the ashes of earlier stars, shining with energy released by the same fusion processes that have powered stars since the first ones ignited billions of years before. And the Sun did not form alone. Earth formed from this same cloud of gas and dust. In the disk surrounding the young Sun, particles collided and stuck together, building up slowly from dust grains to pebbles to boulders to planetesimals, small worlds kilometers across. These planetesimals collided with one another, sometimes shattering, sometimes merging, gradually building up larger and larger bodies. In the inner solar system, where it was too hot for ice to survive, rocky materials dominated. Silicates, metals, the heavier elements forged in stellar cores. From these materials, the terrestrial planets formed: Mercury, Venus, Earth, Mars. Earth grew over tens of millions of years, a violent process of countless impacts, each collision adding more mass, releasing heat, transforming a collection of small bodies into a single larger world. Imagine the young Earth, glowing red with the heat of formation, barely recognizable as the blue world we know today, still in the process of becoming, still gathering itself together from the debris of the early solar system. The young Earth was a harsh place, molten and inhospitable, but it was changing. Over time, Earth cooled enough for oceans and a solid crust. The surface, initially molten from the heat of impacts and radioactive decay, gradually solidified as Earth radiated heat into space. The heaviest materials, iron and nickel, sank toward the center, forming the core. Lighter materials floated to the surface, forming the first crust. And as the planet cooled further, water vapor in the atmosphere condensed and fell as rain that lasted for centuries or millennia, filling the low places in the crust, creating the first oceans. Imagine those early rains, falling on rocks that had never known water, pooling in depressions, slowly covering more and more of the surface until Earth transformed from a mostly dry world to one where water dominated the surface. These oceans would prove crucial. They moderated temperature, enabled chemical reactions, and eventually provided the environment where life could begin. The Earth was becoming a home, a place where complexity could flourish, where chemistry could become biology. None of this would have been possible without that long history we've traced together. Heavier elements made rocky planets possible. The carbon, the silicon, the iron, the oxygen that makes up our planet, all of it was created in stars and scattered into space by supernovae. The early universe, with only hydrogen and helium, could not have made Earth. Rocky planets required billions of years of stellar processing, generation after generation of stars creating and dispersing heavier elements, gradually enriching the galaxy's gas clouds until worlds like ours could form. You're standing, or lying, on the product of billions of years of cosmic evolution, on a planet made possible by countless stars that lived and died before the sun was born. The ground beneath you is made of stardust, atoms forged in stellar furnaces, and brought together by gravity into this particular world, orbiting this particular star, in this particular corner of the galaxy. And then came the most remarkable development of all. Life eventually appeared on Earth. We don't know exactly when, perhaps 3.8 billion years ago, perhaps even earlier, but at some point in those ancient oceans, chemistry crossed a threshold into biology. Simple molecules organized themselves into more complex ones. Somehow, self-replicating systems emerged, patterns of matter that could maintain themselves and make copies. These first living things were simpler than the simplest bacterium today, but they had the essential quality of life. They could reproduce, they could evolve, they could respond to their environment. From these humble beginnings, through billions of years of evolution, through countless generations adapting and changing, life diversified into the magnificent variety we see today. Every living thing on Earth, from bacteria to blue whales, from redwood trees to humans, shares a common ancestor that lived in those ancient oceans. You are part of that story, a continuation of a lineage that has persisted unbroken for billions of years, adapting and surviving through ice ages and asteroid impacts, through continental drift and climate change. Life is the universe becoming aware of itself, matter organizing itself to the point where it can contemplate its own existence. And as you lie here, drifting towards sleep, you are participating in that ancient pattern, your body running on chemistry that traces back to those first living things in Earth's primordial seas. Rest in that connection. Feel yourself as part of this immense story, a temporary pattern in the flow of atoms and energy, but a pattern connected to everything that came before, part of the universe's long journey, from simple to complex, from darkness to light, from matter to mind. As you continue to float through this cosmic story, consider that the universe is not a static place, frozen in time, but a living tapestry of constant change. Stars shine by turning hydrogen into helium. This is the fundamental process that powers every star you see in the night sky, the same process happening in our sun at this very moment. Deep in stellar cores, where temperatures reach millions of degrees and pressures are immense beyond imagining, hydrogen nuclei overcome their natural repulsion and fuse together, combining to form helium. Each fusion releases a tiny burst of energy, and the countless trillions upon trillions of these reactions happening every second create the steady outpouring of light and heat that we call starlight. This is a slow burning, a controlled fusion that can continue for billions of years, converting mass into energy according to Einstein's famous equation. The sunlight that warmed your skin today began as fusion reactions in the sun's core, energy that took thousands of years to work its way from the center to the surface before finally streaming across space to reach Earth. Every star in the sky is doing this same patient work, turning the simplest element into something slightly more complex, releasing light as they do, illuminating the cosmos one fusion reaction at a time. But not all stars burn at the same rate, and herein lies a beautiful irony of stellar life. Massive stars burn fast and die young. Those brilliant giants, the ones hundreds of times more massive than our sun, the ones that shine with the luminosity of 100,000 suns. They squander their fuel quickly. Their immense gravity compresses their cores to tremendous pressures and temperatures, driving fusion at furious rates. They shine brilliantly, yes, but briefly. A star 100 times the sun's mass might last only a few million years before exhausting its fuel and exploding as a supernova. These are the cosmic mayflies, spectacular but ephemeral, racing through their life cycles while smaller stars have barely begun their journey. There's something almost poignant about these massive stars. They burn so brightly precisely because they're burning themselves out, their very brilliance ensuring their quick demise. Like a candle flame that burns twice as bright and half as long, they light up the cosmos but cannot sustain themselves indefinitely. Meanwhile, the universe is patient with its smallest members. Small stars can last longer than the current age of the universe. A red dwarf, a star with only a tenth of the sun's mass, burns its hydrogen so slowly, so conservatively, that it could shine for 1 trillion years or more. Think about that. The universe is only 13.8 billion years old, but the smallest stars could potentially last for 10 trillion years. Not a single small red dwarf that has ever formed has yet died of old age. Every small star that ignited in the early universe is still shining today, and will continue shining long after our sun has died, long after most of the stars you can see tonight have exhausted their fuel. These dim, unassuming stars will be the last lights in the universe, still burning steadily when almost everything else has gone dark. There's something comforting about that. The quiet, modest stars outlasting the brilliant giants, persistence triumphing over spectacle, the gentle glow continuing long after the bright flash has faded. And it's not just stars that change over cosmic time. Planets and moons change over billions of years. The Earth you know today, with its green continents and blue oceans, is just one moment in a long story of transformation. Continents drift across the surface, colliding to form mountain ranges, splitting apart to form new oceans. The atmosphere has changed dramatically. Earth's early atmosphere had no oxygen, and it was only after photosynthetic life evolved that oxygen began to accumulate, fundamentally transforming our world. Mars may once have had rivers and lakes, but lost most of its atmosphere and became the cold desert we see today. Venus might have once been more temperate, but a runaway greenhouse effect turned it into a hellish world of crushing heat and pressure. Moons like Europa and Enceladus, orbiting in the cold outer solar system, may hide oceans beneath their icy crusts, warmed by tidal heating from their giant planet hosts. Even our moon, seemingly unchanging in the night sky, is slowly drifting away from Earth, a few centimeters per year, gradually altering the length of our days. Nothing in the cosmos is truly permanent. Everything evolves, everything changes given enough time. This ongoing transformation means that habitability itself is not permanent. Some worlds may shift between habitable and hostile conditions. A planet might start with the right temperature, the right atmosphere, liquid water on its surface, all the ingredients for life, but slowly change as its star evolves, as its atmosphere escapes into space, as volcanic activity wanes and its magnetic field fades. Or the reverse might happen. A frozen world might become habitable as its star brightens with age, or as tidal heating from a giant neighbor melts its ice. There may be worlds out there that were habitable billions of years ago, but are barren now, and worlds that are barren today, but will become habitable billions of years hence. Life, if it arises, must adapt to these changing conditions or perish. This is the universe's way. Nothing stays the same, nothing is guaranteed, everything flows and changes. And yet within this constant change, patterns persist, structures maintain themselves, and life, when it finds a foothold, proves remarkably resilient and adaptive. As you drift towards sleep, imagine the universe as it truly is, not a museum of static objects, but a living cosmos, constantly changing, constantly evolving, stars being born and dying, planets forming and transforming, matter and energy flowing in their eternal dance. Everything connected, everything in motion, everything part of one vast, unfolding story that continues even now, even here, even in this quiet moment as you rest. Now let yourself shift perspective, from the universe itself to humanity's gradual awakening to cosmic truth. For most of human history, we looked up at the night sky and saw mystery. For centuries, people believed the Milky Way was the entire universe. That pale band of light stretching across the night sky, that river of stars visible on clear, dark nights. Ancient observers thought this was all there was. Everything that existed, they believed, was contained within this great wheel of stars, with Earth at or near the center. It was a universe of comprehensible size, bounded and complete. Philosophers and astronomers mapped the stars, noted their patterns, tracked the planets wandering among them, but the fundamental scale of things remained hidden. They could see fuzzy patches of light scattered among the stars. Nebulae, they called them, from the Latin word for cloud, but these were thought to be clouds of glowing gas within our own stellar system, not separate realms beyond our own. The universe, in humanity's understanding, was vast but finite, grand but knowable. Rest in that earlier worldview for a moment, imagining a cosmos limited to what could be seen, a universe that was large, but not incomprehensibly so. But careful observation, patient measurement, and new technologies gradually revealed a different truth. Observations of distant stars proved other galaxies existed. In the early 20th century, astronomers turned increasingly powerful telescopes on those fuzzy nebulae, particularly a prominent one in the constellation Andromeda. By studying individual stars within these nebulae, specifically certain variable stars whose brightness changes in predictable ways, they could measure distances. And the distances they calculated were staggering. These nebulae weren't within the Milky Way at all. They were separate collections of stars, separate galaxies, each containing billions of suns, lying at distances so vast that their light had traveled for millions of years to reach Earth. The universe suddenly became vastly larger. The Milky Way, humanity's entire known universe, was revealed as just one galaxy among countless others, an island of stars in a much vaster ocean. Imagine the intellectual shock of that realization. The sudden expansion of the known cosmos, the humbling recognition that our entire stellar neighborhood was just one small part of something unimaginably greater. And then came an even more surprising discovery. In the 1920s, Edwin Hubble discovered galaxies are moving away from us. Using spectroscopy, analyzing the light from distant galaxies, Hubble noticed something remarkable. The light was shifted toward the red end of the spectrum, and the degree of this redshift increased with distance. This was the Doppler effect, the same phenomenon that makes a siren's pitch drop as an ambulance speeds away from you. The galaxies were receding, moving away from us through space. And more remarkably still, the farther away a galaxy was, the faster it was moving away. This wasn't random motion. There was a clear relationship between distance and velocity. Galaxies twice as far away were moving away twice as fast. Galaxies at 3 times the distance were receding 3 times as quickly. This pattern suggested something profound was happening, something beyond simple motion through space. Hubble's careful measurements, his meticulous observations of galaxy after galaxy, revealed a cosmic truth that no one had anticipated. The implication was unavoidable and revolutionary. This showed the universe is expanding. Space itself was growing, stretching, carrying galaxies along with it like raisins in a rising loaf of bread. Galaxies weren't moving through space. Space was expanding between them. Every region of the universe was moving away from every other region, with no center to the expansion, no special place from which everything was fleeing. This was something entirely new to human thought. Not objects moving through a static container, but the container itself growing, the fabric of space itself stretching over time. The universe, it turned out, was not a static stage on which matter moved, but a dynamic entity itself, evolving, changing, expanding continuously. Let yourself imagine that, all of space growing, all the distances between galaxies increasing moment by moment, the universe becoming larger as time flows forward. And if the universe was expanding now, if space was growing, then running time backward led to an inescapable conclusion. Expansion revealed the universe had a hot, dense past. If galaxies were moving apart now, they must have been closer together in the past. Continuing further back, there must have been a time when all matter and energy was compressed into a smaller volume. Further still, hotter, denser, more compact. Following the mathematics and observations to their logical conclusion led to the Big Bang, to that moment of beginning we explored at the start of our journey. The expansion of the universe wasn't just an interesting fact about the present. It was a window into cosmic history, evidence written in the motion of galaxies that revealed the universe's origin story. Everything we've discussed tonight, the hot beginning, the formation of elements, the birth of stars and galaxies, all of it was implied by Hubble's observations of those distant, receding galaxies. The universe had revealed its own history to patient observers, written in light that had traveled for billions of years to reach our telescopes. And so humanity learned its place in the cosmos, not through revelation, but through careful observation, through the patient accumulation of evidence, through the willingness to follow where the data led even when it challenged everything previously believed. As you rest now, consider how far our understanding has come, how much we've learned about the universe and our place in it, and how much mystery still remains, waiting to be discovered by future generations looking up at the same stars we see tonight. But how do we know all this? How can we speak with confidence about billions of years, about the universe's age, about events that happened long before Earth existed? Let yourself consider the methods, the patient detective work that lets us measure cosmic time. Scientists estimate the universe's age by measuring its expansion rate, by observing how fast galaxies are moving away from us, by measuring the relationship between distance and recession velocity that Hubble first discovered. Astronomers can calculate something called the Hubble constant, a number that describes how quickly the universe is expanding right now. And here's the elegant part. If you know how fast the universe is expanding today, and you assume it's been expanding all along, you can work backward to find when everything must have been in the same place. It's like watching a film in reverse, watching scattered objects come together, calculating when they must have started from a single point. The math isn't quite that simple. The expansion rate has changed over time, affected by gravity and mysterious forces we'll talk about later. But the principle holds. By measuring expansion today, we can estimate when expansion began. Current measurements give us that figure we started with, about 13.8 billion years, the time since the Big Bang, the age of everything. But good science doesn't rely on a single method. They cross-check this using globular clusters, some of the oldest stars known. Scattered around the Milky Way and other galaxies, these dense spheres of ancient stars contain some of the earliest stellar generations. By understanding how stars age, how they burn through their fuel, how their brightness and color change over billions of years, astronomers can estimate the age of individual stars. And the oldest stars in globular clusters, dim, cool red dwarfs that have been burning slowly since near the beginning, appear to be about 12 to 13 billion years old, comfortably consistent with the universe being 13.8 billion years old. These stars formed early in the universe's history, and they've been shining ever since, serving as cosmic timepieces, their very existence confirming our calculations about the universe's age. There's something reassuring about this convergence of methods. Expansion measurements and stellar ages, both pointing to the same time frame, different approaches to the same question yielding consistent answers, our understanding confirmed through multiple independent lines of evidence. And we can look even further back, to evidence written in the very structure of space. The smoothness of the CMB supports the idea of inflation. Remember that ancient light we discussed, released when the universe became transparent 380,000 years after the Big Bang? When astronomers map the cosmic microwave background across the entire sky, they find it remarkably uniform. The temperature is the same in all directions to within a few thousandths of a degree. This smoothness is puzzling if you think about it carefully. Regions of the universe that are now on opposite sides of the observable universe, separated by distances so vast that light hasn't had time to travel between them since the beginning, somehow have almost exactly the same temperature. How could they be so similar if they've never been in contact? Inflation explains this beautifully. If there was a brief period of exponentially rapid expansion very early on, regions that are now vastly separated were once close together, in thermal contact, able to reach the same temperature before inflation pulled them apart. The smoothness of the CMB is like a fingerprint left by inflation, evidence of that extraordinary first fraction of a second when space expanded faster than light could cross it. Our ability to observe the universe has limits, but these limits themselves teach us something profound. The observable universe is limited by how far light has traveled. Since light moves at a finite speed, fast but not instantaneous, and since the universe has a finite age, there's a limit to how far we can see. Light from anything more than about 13.8 billion light-years away simply hasn't had time to reach us yet. This creates a kind of cosmic horizon, a boundary beyond which we cannot see, not because there's nothing there, but because the light hasn't arrived. The universe likely extends far beyond what we can observe, perhaps infinitely far, but we're limited to seeing only a sphere around us, centered on Earth, with a radius defined by light travel time and the universe's expansion. This observable universe contains hundreds of billions of galaxies, each with hundreds of billions of stars, an almost incomprehensible richness. And yet it may be only a tiny fraction of the whole cosmos. We're like someone standing on an island in a vast ocean, able to see only to the horizon, knowing that more ocean lies beyond, but unable to see it directly. And this limitation gives us a remarkable gift. Looking farther away means seeing earlier times. When you look at a distant galaxy a billion light-years away, you're not seeing it as it is now. You're seeing it as it was a billion years ago, when the light that's reaching your eye tonight first began its journey across space. Look at a galaxy 10 billion light-years distant, and you're seeing it as it was when the universe was less than a quarter of its current age, when our Milky Way was still forming, long before the Sun was born. The most distant objects we can observe, ancient galaxies formed when the universe was only a few 100 million years old, show us the universe in its infancy, still hot and dense, still in its formative stages. Telescopes are time machines, letting us look into the past, observe cosmic history directly, watch the universe evolve. The farther we look, the further back we see, until we reach that limit, the cosmic microwave background, the light from when the universe became transparent, our ultimate horizon. Everything we've discussed tonight, the Big Bang, the first stars, the formation of galaxies, isn't just theory or speculation. We've observed these things, seen them frozen in the light from distant objects, watched cosmic history unfold across billions of years, captured in a single image. And as you drift towards sleep, let yourself imagine that, the universe revealing its own past, light carrying messages across cosmic time, every distant star and galaxy a window into history, the whole story of creation written in the sky for those patient enough to observe and wise enough to understand. Now bring your awareness back to the present moment, to the universe as it exists right now, tonight as you rest. The universe is still expanding. Everything we've discussed about cosmic growth, about galaxies moving apart, about space stretching, this isn't something that happened only in the distant past. It's happening now, continuously, moment by moment. While you sleep tonight, the space between galaxy clusters will grow just slightly larger. Over your lifetime, the universe will expand by a tiny fraction of a percent, imperceptible to human senses, but real and measurable with our instruments. The expansion that began with the Big Bang never stopped. Galaxies continue to recede from one another, space continues to stretch, the universe continues to grow. It's a process as fundamental to the cosmos as breathing is to life, a rhythm that's been continuing for 13.8 billion years and shows no sign of stopping. The universe you'll wake up to tomorrow will be slightly larger than the one in which you're falling asleep tonight, though the difference will be far too small to notice. Everything is in motion, everything is growing, the cosmic expansion continues its patient work. But astronomers discovered something unexpected, something that surprised even those who had accepted the expanding universe. That expansion is speeding up. In the 1990s, by observing distant supernovae, exploding stars that serve as cosmic distance markers, scientists found that the universe's expansion rate has not been slowing down as they expected, but rather accelerating. Galaxies are moving apart faster now than they were billions of years ago. This was shocking because gravity should slow expansion down, should be pulling everything back together, or at least reducing the speed at which things fly apart. Instead, something is counteracting gravity, pushing space to expand faster and faster over time. Imagine throwing a ball upward, and instead of slowing down as it should, watching it accelerate away from you, moving faster and faster the higher it goes. That's what's happening with cosmic expansion. The universe isn't just expanding, it's expanding at an increasing rate, driven by something we don't fully understand, something working against gravity's inward pull. Scientists have given this mysterious influence a name. A mysterious force called dark energy drives this acceleration. The name is admittedly a placeholder, a label for our ignorance more than genuine understanding. Dark, because we can't see it, can't detect it directly, know it only through its effects on cosmic expansion. Energy, because it seems to be a property of space itself, a kind of pressure or tension inherent in the vacuum, causing space to push outward against gravity's pull. It's everywhere, filling all of space uniformly, and unlike matter or radiation, it doesn't dilute as the universe expands. The same amount of dark energy exists in each cubic meter of space regardless of how space grows. This makes it increasingly dominant over time. In the early universe, matter was dense enough that its gravity overwhelmed dark energy's effects. But as expansion continued and matter spread out, dark energy's influence grew relatively stronger. Until about 5 billion years ago, it became the dominant force, and expansion began to accelerate. We don't know what dark energy is, don't understand its fundamental nature, can only measure its effects and calculate how much there must be to explain what we observe. It remains one of cosmology's deepest mysteries, a reminder of how much we still have to learn. And dark energy isn't alone in our ignorance. Dark matter and dark energy make up about 95% of the universe. Think about that remarkable statement. Everything we can see, all the stars, all the galaxies, all the nebulae, all the planets, all the matter that interacts with light in any way we can detect, accounts for only about 5% of the universe's total content. About 27% is dark matter, that invisible scaffolding we discussed earlier, detectable only through its gravitational effects, holding galaxies together and shaping the cosmic web. And about 68% is dark energy, that mysterious force driving accelerated expansion. The ordinary matter that makes up everything we know, the atoms in your body, the air you breathe, the earth beneath you, all the stars in the sky, is a small minority, a thin veneer on a cosmos dominated by things we can't directly observe. We live in a universe where most of reality is hidden from us, where the visible is dwarfed by the invisible, where the light we see illuminates only a small fraction of what exists. This leads to a humbling realization. Most of reality is invisible to us. We walk through a cosmos largely beyond our direct perception, surrounded by dark matter whose gravity we feel but cannot see, embedded in a space filled with dark energy we cannot detect except through its grand effects on cosmic expansion. It's like being a fish unaware of the water it swims through, or like perceiving only one color of a vast spectrum. The universe we observe directly, spectacular as it is, rich with galaxies and stars and nebulae, is just the tip of an iceberg, the visible portion of something much grander and stranger than we can fully observe. And yet, remarkably, we've learned about these invisible components anyway, through careful observation and reasoning, through noticing what they do even if we can't see what they are. Gravity reveals the presence of dark matter. The motion of galaxies reveals dark energy. We deduce the invisible through its effects on the visible, like a detective inferring the presence of someone who's left the room by the traces they left behind. This should give us both humility and confidence. Humility because so much remains unknown, confidence because we've proven capable of discovering truths about reality that lie beyond direct observation. As you rest in the darkness of night, in a room where much is invisible in the shadows, reflect on this. The universe too has its shadows, its hidden aspects, its mysteries that remain to be solved. And within those mysteries, within that vast invisible majority of reality, may lie wonders we haven't yet imagined, waiting patiently for future generations to discover, to name, to understand. Let yourself drift now, floating in a universe mostly unseen, connected to invisible currents of dark matter and dark energy, part of a reality far stranger and more magnificent than simple appearances suggest. Now let your mind drift forward instead of back, into times yet to come, into the deep future of the cosmos. The universe's story doesn't end here, in this present moment. It continues forward, evolving, changing, following the laws of physics into eons we can only imagine. Over time, distant galaxies will drift beyond our view. As dark energy drives accelerated expansion, as space stretches faster and faster, galaxies that we can see today will gradually recede beyond a critical threshold. Their light will become so redshifted, stretched to such long wavelengths, that it will fade from detectability. More dramatically, the most distant galaxies will be carried away so quickly by expanding space that their light will never reach us. New light leaving them today will be unable to overcome the expansion, will be swept backward like someone trying to swim against a current too strong. One by one, starting with the most distant and progressing to those closer, galaxies will disappear from our observable universe, crossing beyond our cosmic horizon, passing into a region of space forever beyond our ability to see. The universe won't actually become smaller. Those galaxies will still exist, still shine. But from our perspective, they'll simply vanish, their light no longer able to bridge the growing gulf between us. And even the familiar will change. The night sky will slowly change as stars move. The stars we see aren't fixed in place like paint on a celestial dome. They're in motion, each following its own orbit around the galactic center, each with its own velocity through space. From our perspective, these motions are imperceptibly slow. The stars appear fixed in the same patterns our ancestors saw thousands of years ago. But over tens of thousands of years, over hundreds of thousands of years, the stars will drift relative to one another. Bright stars will dim as they move farther away. New stars will drift into prominence as they pass closer to our solar system. The whole familiar pattern of the night sky will gradually shift and change, as inexorable as the movement of continental plates on Earth, as patient as geological time. In 100,000 years, an observer from Earth, if Earth and humanity still exist, will look up at a sky noticeably different from the one we see tonight, the stars rearranged, the familiar made strange. This means something poignant about the patterns we see. Constellations are temporary patterns. The Big Dipper, Orion, the Southern Cross, these shapes that cultures have recognized and named and woven into stories for thousands of years, are cosmic coincidences, temporary arrangements of stars that happen to lie in roughly the same direction from Earth, but are often at vastly different distances. The stars in Orion's belt, for instance, are not actually close together in space. They simply appear aligned from our viewpoint. And this alignment is temporary. In the deep past, these stars were in different positions relative to each other. In the deep future, they'll drift apart, and the constellation will dissolve. The hunter will lose his form. The dipper will spill. The cross will lose its symmetry. Future humans, if they look up at all, will see different patterns, will create different constellations, will tell different stories about different shapes formed by different stars. The sky we know is just one moment in an ongoing rearrangement, a single frame in a very slow cosmic film. And the long-term trend is toward emptiness. Our view of the universe will grow emptier. Not immediately, not in thousands or millions or even billions of years. But given enough time, given trillions of years, the accelerating expansion will carry away almost everything we can currently see. Distant galaxy clusters will disappear first, then individual galaxies beyond our local group, then more and more until only the galaxies gravitationally bound to our own. The Milky Way, Andromeda, and a handful of smaller companions, likely merged by then into a single giant elliptical galaxy, will remain visible. An observer in this distant future will look out from their galaxy and see almost nothing. A few scattered stars within their own galaxy, and beyond that darkness. No distant galaxies, no cosmic web, no evidence of the vast universe we know today. They would have no way to know, from observation alone, that billions of other galaxies existed beyond their horizon, forever out of reach. The universe will still be vast, but each galaxy or galaxy cluster will be isolated, alone in an expanding void, surrounded by darkness. It's a lonely future. In some ways, the universe growing dark and empty not through death, but through isolation, through space growing so large that light cannot bridge the gaps. Yet even in this distant emptiness, some light will persist. Some stars will outlive galaxies themselves. Those small red dwarfs we discussed earlier, burning their hydrogen so slowly they could last 1 trillion years or more. They will still be shining long after larger stars have exhausted their fuel and died, long after the star formation in galaxies has ceased for lack of gas, long after the universe has grown cold and dark and empty. These dim, patient stars will be among the last sources of light in the cosmos, scattered throughout the darkness, keeping their vigil across unimaginable spans of time. They are the universe's nightlights, the final embers of the age of stars, burning steadily onward through the long twilight of cosmic history. And perhaps around some of these stars, if any planets remain, if any consciousness still exists, there will be observers watching their star, knowing it is one of the last lights left, treasuring its warmth in the growing cold. But that future is so distant, so far beyond our current era, that it's almost abstract. Trillions of years away, a time span that dwarfs the entire history of the universe so far. For now, for the next billions of years at least, the universe will remain rich and bright, full of galaxies and stars, a cosmos of light and structure and beauty. Tonight, as you rest, the sky is full of stars, the universe is full of galaxies, and that will remain true for longer than humans can easily imagine. Let the distant future be just a thought, a possibility, an ending written in the equations, but still unfathomably far away. For now, rest in the present universe, rich and full and beautiful, and let yourself drift peacefully into sleep, knowing the stars will still be there tomorrow night, and for countless nights to come. As you settle deeper into rest, consider that for all we've learned, for all the cosmic history we've traced together tonight, we haven't reached the end of understanding. Far from it. The universe still holds its mysteries close, still has secrets waiting to be revealed. Some theories suggest the Big Bang may not have been the absolute beginning. What we call the Big Bang, that moment of extreme heat and density from which our observable universe emerged, might itself have been preceded by something else. Perhaps there was a previous universe that collapsed and rebounded, like a cosmic heartbeat, with the Big Bang being a moment of transition rather than creation from nothing. Perhaps our universe emerged from a quantum fluctuation in some higher dimensional space, a bubble nucleating in a larger substrate. Perhaps time itself doesn't extend infinitely into the past, but curves back on itself in ways our everyday intuition cannot grasp. These ideas remain speculative, mathematical explorations of possibility rather than established fact, but they remind us that the question, what came before the Big Bang, may have an answer, or maybe the wrong question entirely, assuming a before that doesn't exist. The deepest questions about origins remain tantalizingly open, waiting for evidence or insight that might shift our understanding once more. And beyond the question of our universe's beginning lies an even more expansive speculation. Other ideas propose a multiverse, though there is no direct evidence yet. Some versions of cosmic inflation, that rapid expansion in the first fraction of a second, suggest that what inflated wasn't just the region that became our observable universe, but a much vaster space, with different regions stopping their inflation at different times, each becoming a separate universe with potentially different physical properties. In this picture, our universe would be one bubble in a vast cosmic foam, surrounded by countless other universes we can never observe or reach. Other theories from quantum mechanics suggest that every quantum possibility might spawn a separate universe where that possibility becomes real. These are grand ideas, captivating to imagine, an infinite array of realities, each with its own laws, its own history, its own possibilities. But they remain firmly in the realm of hypothesis. We have no way, currently, to observe other universes if they exist, no telescope that can peer beyond the boundaries of our own cosmos, no experiment that can confirm or deny these vast speculations. The multiverse remains an idea, intriguing but unproven, a reminder that our theories sometimes outrun our ability to test them. Even our understanding of this universe contains uncertainties. Some research questions whether the universe could be older than current models suggest. While the 13.8 billion year age is well supported by multiple lines of evidence, science is never completely certain, never fully closed to revision. Occasionally, observations seem to show objects or structures that appear older than they should be according to current models, prompting re-examination of assumptions. Perhaps our understanding of how stars age contains subtle errors. Perhaps the expansion history is more complicated than we think. Perhaps there are phenomena we haven't accounted for that affect our measurements. Most likely, the current age is correct or very nearly so. The convergence of different measurement methods is strong support. But the possibility of revision remains, as it must in any honest science. We hold our understanding tentatively, confidently but not absolutely, ready to adjust if new evidence demands it. This uncertainty might seem like weakness, but it's actually a strength, the willingness to question, to test, to potentially overturn established ideas in light of new evidence, is how knowledge advances, how understanding deepens. And our investigation continues actively, in real time. New telescopes continue testing ideas about dark matter and dark energy. The James Webb Space Telescope, launched recently, peers deeper into space and further back in time than any previous instrument, observing the first galaxies in unprecedented detail. Ground-based observatories map the cosmic web with increasing precision, tracking how structure has evolved over billions of years. Experiments deep underground search for dark matter particles, hoping to detect the direct interaction that would prove their existence. Satellites measure the cosmic microwave background with exquisite accuracy, testing predictions of inflation theory. The expansion rate is being measured more precisely than ever, trying to resolve puzzles in our current understanding. Every night, around the world, telescopes point skyward, collecting light, gathering data, slowly building up the observations that will confirm or challenge our theories. Science doesn't stop. It's an ongoing process, a conversation between theory and observation, between prediction and measurement. The answers we have now are our best current understanding, subject to refinement and revision as knowledge accumulates. This means something both humbling and exciting. Much of the universe's story is still unwritten. We know the broad outlines, the Big Bang, the formation of structure, the evolution of galaxies and stars, but countless details remain unclear. How exactly did the first stars form? What is dark matter made of? What is dark energy? Are there other universes? How common is life in the cosmos? How does consciousness emerge from matter? These questions and countless others await answers. Future generations will know things we don't, will understand aspects of the universe that puzzle us today, will look back at our current theories the way we look back at ancient cosmologies, with respect for how much was figured out with limited tools, but aware of how much was missing. And that's as it should be. The universe reveals itself slowly, generation by generation, each new discovery opening new questions, each answer spawning new mysteries. The story we've traced tonight is true as far as we know it, but it's incomplete, provisional, a work in progress. And perhaps that's the most wonderful thing, that despite all we've learned, the universe still holds surprises, still guards secrets, still offers endless opportunities for discovery and wonder. As you drift into sleep now, rest in that openness, that mixture of knowledge and mystery. We know so much, yet understand so little. We've mapped the cosmos, yet missed most of reality. We can trace time back to its beginning, yet wonder what came before. And in that space between knowing and not knowing, in that fertile ground where curiosity grows, lies the continuing adventure of understanding our place in the universe. Sleep well, knowing that the mysteries will still be there tomorrow, waiting patiently to be explored, inviting new generations to look up, to wonder, to question, to discover.